Thank you so much, Vasilis, and thank you so much for the organizers for inviting me. I'm really honored to give this lecture. So my talk today is going to be what's called average case complexity through the lens of interactive puzzles, and it's really going to be about combination of cryptography and complexity and the interplay between the two. So let me start from the beginning. Before jumping into average case complexity, let's start off with the most foundational and important open problem in computer science and maybe even in mathematics today, which is the P versus NP problem, which roughly speaking can be summarized as follows. Is it the case that if a solution to a problem can be efficiently verified, can we also then efficiently find a solution? So a little bit more precisely, the class of problems NP is defined as a set of problems for which solutions, also called witnesses, can be efficiently verified. And by efficiently verified, we mean they can be verified in polynomial time. So a little bit more precisely, we say that a language L is an NP if there exists some polynomial time relation such that an instance is in the language if and only if there exists some witness that certifies that this instance is in the language. Right, so whenever some instance is true, whenever some instance is in language, I can therefore provide a witness, W, that you can efficiently verify by running this polynomial time verifier. And then the question of whether P equals NP boils down to saying, is it the case that all languages in NP can be efficiently decided in polynomial time? So just to very briefly give you some examples of NP problems, perhaps the most commonly known one is Boolean satisfiability. So given some Boolean formula, does there exist a satisfying assignment? Another very famous problem is that of graph recoloring, and let's actually restrict to a planar graph. So I'm giving you a planar graph, so a graph that can be drawn without any edges intersecting or any edges crossing. And the question now is, can I color this graph so that any two nodes that have an edge between them have different colors? And the graph recoloring problem refers to the question of whether it's possible to color this graph with just 3 colors. Right? So these problems are all in NP. You can efficiently verify whether you have a solution. If I give you a coloring, you can check that any two nodes that are connected with an edge have different colors. And you can check that it uses less than 3 colors, or at most 3 colors. And it turns out they're also NP complete, so they're as hard as any other problem in NP. Now, the P versus NP problem might actually not be the main question we're interested in practice. Right? It could be the case that NP is hard on the worst case, meaning that it is actually hard for every algorithm that tries to decide some NP problem, there exists some instances on which it fails. But it could be the case that those instances actually never really arise in practice. So in practice, what we care about is whether we end up with instances that turned out to be hard. Right? And the area of average case complexity tries to exactly address this problem. So rather than looking at trying to solve these NP problems in the worst case, we would have looked at, we consider some kind of samples instances. And we're wondering whether it is the case that when I sample instances from some efficiently samplable distribution, this problem still is hard to solve. Okay, and it could just be the case that in real life, it is the case that the instances we encounter are just turned out to be easy, right? So, a little bit more precisely, we're going to say that a language is hard on the average, or average case hard, if there exists some probabilistic polynomial time sampling algorithm, so some efficient sampling algorithm. It runs in polynomial time but has access to randomness. So this sampler D samples some instances these instances, a large fraction of them should be in the language. So let's say, for simplicity, that 2/3 of the instances are in the language. And I say that this language is hard on average if it is the case that even though many instances are in the language, no probabilistic polynomial time algorithm can actually turn out to find a witness when I sample instances from this distribution. Okay? Does it make sense? So we have some sampler. He sampled some instances. And I'm calling this, this problem hard on average if it is the case that no algorithm, no efficient probabilistic polynomial time algorithm will be able to find witnesses to the sample instances with probability, let's say, 1/3. Okay? So this is one particular definition of hard on average. It's actually not the original definition that Levin proposed. So in this particular definition, we're talking about the task of finding a witness. And in Levin's original definition, he instead considered a decisional problem where the task was instead to decide whether an instance is in the language or not. For my purposes, I'm going to stick to this search problem where the question is to find the witness. And it turns out that this is actually, without loss of generality, these various different notions of hard on average for NP have been studied for a long time, and now we understand that they're all actually essentially equivalent. So in particular, the question of finding a witness versus deciding a language makes no difference, and the definitions are equivalent. So for my purpose, it's going to be just easier to talk about these type of search problems. Right? So let me present this definition yet another time, but using a slightly different language. So syntactically, it's actually going to be exactly the same. It's just using a slightly different language. So I'm going to consider this kind of problem scenario as a game between some challenger C and some attacker A. This challenger C needs to be polynomial time. And what he does first is he samples an instant X. Then the goal of the attacker is to find some witness. And this challenger will eventually accept if indeed the attacker manages to find a witness such that this relation, the witness-NP relation, accepts it. Okay? And for this language to be hard on average, we require two conditions. The first one is a non-triviality condition, which is that whenever C samples this X, with probability at least 2/3, the instance is indeed in language and therefore has a witness. And the hardness condition, just rephrasing what we said before, there doesn't exist a polynomial time attacker that manages to convince the challenger with probability greater than 1/3. Does that make sense? Okay, so this is kind of a game-based way of defining what it means for language to be hard on average. Now, it's clearly very, very widely believed that NP is hard on average. It's kind of a very minimal assumption that we make in complexity theory. Yet, somewhat surprisingly, it is the case that even when we have this NP complete problem, or it turns out that many of them actually can be efficiently solved on many distributions of interest. Right? So there are all these heuristics that seem to do pretty well. So the question I would like to address in this talk is trying to understand what makes an NP problem hard on average. Like, are there some characteristics of the problem that makes it hard on average? Okay. In particular, could it be the case that there are some natural subclasses of problems that make it easy? Okay. In particular, is it the case that maybe I can restrict the class of problems in some natural way, or maybe restrict the class of distributions in some natural way that make the problem easier, right? And that would be a way to understand where this hardness stems from. And indeed, there have been these subclasses of NP that have been defined and studied, and some of them are extremely natural. Okay? And some of them are actually as old as average case complexity itself. So the first thing I would like to talk about is something called total function NP, or TFNP. So TFNP is a subset of NP problems where it is the case that actually every instance has a witness. Okay, and I'm going to go over this in a lot more detail in the next few slides. So this is a way to restrict the class of NP languages, because right now we're restricting it to problems where every instance has a solution. But I can also restrict the distribution. Okay, so I'm not going to restrict the language necessarily, but now instead let's consider some more natural distributions. And in fact, the notion of a one-in function that's commonly used in cryptography can be viewed as equivalent to consider a hard-of-average language in NP, where I consider a very restricted distribution. In particular, distributions where not only the challenger is sampling an instance, but also one where the challenger is sampling an instance together with a witness. So could it be the case that for those type of distributions, the problem becomes easier? All right, so let me in fact go over both of these two things in more detail, and then we'll take it from there. Okay, so let's start with the TFNP. So TFNP, as I mentioned, is the class of languages in NP where it is the case that in fact every instance is true and every instance has a witness. Right? So a language is in TFNP if it is the case that for every X there actually exists a witness that makes it satisfied. But it could still be hard to find this witness. Right? So we're restricting to these type of languages where everything is true, everything has a witness, but could it still be the case that it's still hard to find it? And indeed, in fact, we do believe that TFNP is hard on average, or at least that TFNP has instances that are hard on average. Before I give you some examples of problems in TFNP, let me just go over TFNP using this game-based worldview instead. So TFNP, well, remember the previous way we looked at average case NP, we have this challenger, he samples some instance, and then you're supposed to respond with a witness. And we had these two conditions, non-triviality and hardness. Non-triviality said that with probability at least 2/3, the challenge needs to sample an instance that's true. Okay. Right now we can get rid of this thing because we're restricting to languages where every instance is true. And so that's what the totality condition says, that in fact, for every X, there always exists some witness. Yeah.
This language has only true statements, right?
Yeah. All right, so now we're considering a scenario where he samples some X. For every X, there exists a witness, and the task is for you to find it. Okay, this seems to make the problem a lot easier. Right? All right, let me give you some examples of things in TFNP. So one very nice example, which is a close variant of graph 3 coloring, is graph 4 coloring. Okay? So in the graph 4 coloring problem, it's exactly as before. I'm giving you some planar graph, and the question is, can you color it in 4 colors? This is a problem that's been actually studied for a long time, and in 1852, Francis Guthrie conjectured, in fact, the answer is always yes. For every planar graph, you can, in fact, color it with 4 color. And that was actually first proven in 1976. So the answer actually is yes. So for every planar graph, there always is a 4 coloring. But the question is, how do you find it? Okay. So that's one nice, curious problem. As far as I know, it doesn't really have any particular practical applications, because at least according to Wikipedia, most real-life maps can actually be done in 3 colors anyway. So. But it's cool. That's, you know, we tweak it a little bit, and now you have a problem in TFNP. So here is something that's a little bit more practical in today's world. So machine learning. Okay, one of the key things in machine learning today is a method called gradient descent, which is a particular instance of what's referred to as local search. So in local search, you can kind of abstract the problem of local search as follows. I'm going to give you 3 algorithms. One init algorithm that starts by giving you some initial solution. Then you have a neighbor algorithm that, given some initial solution, gives you a set of neighboring solutions. And then you also have a cost function. So all these things are polynomial time computable, polynomial size circuits that I'm giving you. And your goal is to find a local minimum. So that is some kind of, some instance x, such that for every neighbor, the cost is no smaller. Okay? So why does something like this always have a solution? Well, as the picture there suggests. Let's say you start there, then you look at all your neighbors and you find one that is, take the one that has the smallest cost, and then you go there. Okay, from there you take one that has the smallest cost, and so on and so forth, and eventually you have to come to a node that doesn't have any neighbors with smaller cost, because otherwise, you run out of different costs. So local search clearly is a very useful thing, and here we're guaranteed that a solution always exists. Okay. Let me move on to another very famous instance of a set of problems in TFNP, which is the Nash Equilibrium problem. So I'm giving you a game. I'm giving you a description of a game. And the task is for you to find a Nash equilibrium. I'm not going to go into defining what a Nash equilibrium is, but a very celebrated result by John Nash from 1951 states that, in fact, every finite game has a Nash equilibrium. Okay? But the question is, how do we find it? And this is actually one of the most celebrated problems in TFNP. It turns out that the Nash equilibrium problem is complete for a subclass of TFNP called PPAD. And people are still actively working on trying to prove hardness of PPAD under various cryptographic assumptions. All right, so what I've hoped to have conveyed so far is that even though we're restricting the set of languages to those where every instance is guaranteed to have a solution, we're still considering a very natural class of problems. And in fact, many things of interest fall into this thing. And for many of them, we believe them to be hard. So an important open problem is it the case that these problems in TFNP are actually as hard as general NP problems on average? So in particular, is it the case that if NP is hard on average, then TFNP is also hard on average? Right? Or another way of stating it, is it easier to solve problems when you're guaranteed that they have a solution? So there is evidence both for and against. Okay? So evidence against is, in fact, graph 4 coloring. Not long after they managed to prove that every planar graph is 4 colorable, turned out that they also managed to get efficient algorithms. Okay? And they were maybe not very efficient first, they became even more efficient later. So that thing can be done efficiently. And somewhat intuitively, it seems like, look, if you know that a theorem has a solution, has a proof, then it seems easier to find it, right? You know that you're not just going down the wrong path. You know that there exists a proof. You're going to work harder and maybe find some, I don't know, right? Just intuitively, it seems should be easier. Now, evidence for these implications, we also have that. In fact, already the original paper by Megiddo and Papadimitriou showed that if NP is hard, then it's also hard to find kind of a canonical solution for a TFNP problem. So if there exists a particular type of, for instance, if you look at this local search issue, if your goal is to find a particular solution, in that case it becomes hard. But that's not really what we're after, right? We would like to just consider the problem of finding some solution. And there was some very nice recent progress 2 years ago, where Hubacek, Naor, and what? I'm blanking, yeah. prove the implication. They prove this implication under some complexity conjecture, in particular some kind of de-randomization conjecture. I'm not going to go into exactly what the de-randomization conjecture is, but it's something saying that exponential time computations cannot be significantly sped up by circuits that have access to something called sigma 2 gates. It's a de-randomization conjecture, and under that assumption, this can be proven. Okay.
Question. So we know that if one-way functions exist, then there exist hard on average languages for NP. But I guess we don't know if the same result holds, namely whether if one-way functions exist, do we have any hard on average problems for TFNP? Or
it's a great question. We don't know. Okay. In fact, that's going to be the next thing I'm going to talk about is this problem of one-way functions. Okay. But indeed, if one can solve your problem, that would be a major breakthrough, and I'll get to that shortly. All right, so now the second class of restriction we're going to look at is, instead of restricting a class of MP problems, we're going to restrict the class of distributions. Okay? So, in fact, one of the original motivations for studying average case complexity came actually from cryptography. Okay, and in cryptography, it's not usually not enough to just say there exists some distribution that's hard on average, but we also require it to be possible that to sample these instances that are hard together with a solution, right? So let's look at, so with a picture, maybe there's a case that random instances, they look like this, they're very hard. And when I asked my son to draw a labyrinth with a solution, then this is what he came up with. And as you see, it's like, if I come up with an instance with a solution, it becomes much easier to solve intuitively, right? So let's rephrase this thing again as this game-based using this game-based view. So I have now a challenger. The challenger is going to run this sampler D, and this sampler is going to output an instance X and a witness. Okay, that's the job of the sampler. And we require now that, in fact, this sampler needs to always output a correct witness. Right? So it always samples some X and a witness. Then the challenger doesn't actually output this witness, it just has it there, and it just outputs the instance X, and now your job is to find the witness. Okay? So for reasons that are going to become clear pretty soon, it's going to be important for me to just write down the randomness of this sampler. So this sampler takes some randomness R as input, and it outputs this X and W. Okay? So now this non-triviality condition is replaced by saying the sampler takes some randomness, outputs some X and W, that is where the W is a correct witness. And we now have the same hardness condition before, that no attacker should be able to, no polynomial attacker should be able to recover the witness. Now, let me point out that this somewhat looks similar in some ways to TFNP. And it's actually indeed quite related, but different. And this was already pointed out in the original paper by Megiddo and Papadimitriou. So note here that the sampler here, he always picks instances that are true, right? Because he knows a witness to them. He needs to pick an instance and a witness. So the instance X is always true also. But it's not the case that every X necessarily has a witness. Right? So even though it is the case that he's always picking instances that are true, this is not a problem in TFNP, because it's not the case necessarily to the language, that for the language you have the case that every X has a witness. Okay? So Megiddo and Papadimitriou refer to these type of problems as promised TFNP problems. They're not exactly TFNP. Okay. So this notion of sampling with a witness, as I already mentioned, is very, very close related to the notion of a one-way function. That's really key in cryptography. So let me define the notion of a one-way function, and then we'll see why this is actually exactly the same thing as the notion of Hardness average when I sample with a witness. So a one-way function is a function f that can be efficiently computed, but that should have the property that it's hard to invert it. So let's look at it as this game. So now the challenger samples some random r. He computes the function to get some output y. And the attacker's job is to find some pre-image r prime such that f of r prime equals to y. Doesn't necessarily be exactly the same one, just needs to find some pre-image. And the hardness condition here is that no attacker should be able to win in this game with probability again greater than 1/3. So in other words, no efficient attacker can invert this function. Turns out that this is actually exactly equivalent to the previous definition. The existence of one-way functions is equivalent to the existence of an NP language where you can sample, where the distribution samples an instance with a witness. And well, one direction is trivial. If I have a one-way function, then clearly this gives rise to a distribution when I'm sampling y. Y is the instance, and your job is to find a witness, a pre-image. Right? So a one-way function clearly gives rise to an instance where I'm sampling an instance with a witness. But the other direction is also very easy to see. So if I have this type of language that's hard on average with respect to distribution of my sample instance with a witness, then I can view the distribution D, or the sampling algorithm for the distribution, as a one-way function also. So to do that, it would be useful to just decompose D into two parts. So first, this D, let D1 be the first output of D, and let D2 be the second output, the witness. In that case, I claim that this D1 actually is a one-way function. Because if it wasn't, if it was the case that given X you could recover and find the randomness R, then clearly you can go back to R and then recompute W, and then you're done. Okay. So really, one-way functions, the existence of one-way functions is really exactly the same thing as the existence of a hard and average language, where we're saying it's hard to sample, hard to find witnesses to instances that have been sampled together with a witness. Now, in crypto, this definition is somewhat weak because we're just saying it's hard to find a pre-image with a probability greater than 1/3. In cryptographic applications, you really want it to be, the probability for inverting should be much smaller. Indeed, this difference is not really substantial. You can always amplify the hardness using what's called Gauss hardness simplification theorem. There's also a minor issue regarding infinitely often versus almost everywhere. Let me just ignore it. You can look in the paper for more details. So one-way functions are one of the most crucial cryptographic primitives. In fact, I would say it's easily the most important today and most central cryptographic primitive. They are, we have loads of different candidate constructions of one-way functions. So we have, really believe that one-way functions exist, and in fact, we really hope they do, because they're equivalent to all these other cryptographic primitives that we care about, like encryption schemes, pseudorandom generators, pseudorandom functions, digital signatures, commitments. Basically, most of the key cryptographic primitive are equivalent to the existence of one-way functions. Okay, so that gives rise to the second open problem. Which dates back to this original work by Diffie-Hellman from 1976. Is it a case that we can base the existence of one-way function on some kind of a hardness of NP? In particular, could we say that if NP is hard on average, we can also get a construction of a one-way function? Right? This would be one of the dream problems in cryptography, to base one-way functions on NP being hard on average. And another way of saying it, is it the case that solving problems that are sampled with a solution, is that easier than just solving random problems?
Do we have any proof of barriers for this problem? For example,
Okay, so evidence against, well, one evidence is that intuitively again, like, Isaac's, my son's puzzle here seemed clearly easier to solve than that thing I got from the internet, right? And indeed, there are various ways you can formalize this thing using some kind of notions of black box separation. There are various different black box separations that kind of indicate that it would be hard to prove such an implication. And in fact, there are black box separations also between TFNP and an average case hardness of NP also. I should have probably mentioned that. We also have some evidence for, in a similar style to what was done before by the result of Hubacek et al. And there are these very nice results going back all the way to the 90s showing that if we have something called zero knowledge for NP, then it is the case that if NP is harder than average, then we also have one-way function. Okay, and you can also base it on indistinguishable obfuscation. Both of these two things are kind of orthogonal to NP being harder than average. In particular, if NP is equal to P, zero knowledge for NP exists trivially. So, so we have some assumptions that are believable under which this implication is true. Okay, so this takes me to the main result that I'd like to talk about today, or at least give some intuition about, which is our result. We are not able to solve either of these problems. Okay, we would love to. That would be awesome, and I hope somebody will one day. But what we can say is that the answer to at least one of them is yes. Okay, could be that both are yes. I hope so. Okay, but right now, at least for one of them, the answer is yes. So in particular, the theorem that we prove is that if NP is harder than average, then that implies either that TFNP is harder than average, or that one-way functions exist. Okay. So another way of stating this is in the language of Impagliazzo. So Impagliazzo consider various different possible worlds out there, and one of them was called Pesiland. Pesiland, according to him, was the worst of all possible worlds, at least in complexity theory. Okay, and so Pesiland is a world where NP is harder than average. So meaning that if we would like to solve these NP problems in real life, we really need to, we cannot expect to have general purpose algorithms. They're going to do well, and in general, it's going to be hard, right? But one-way functions don't exist, so we don't have cryptography, right? So algorithms are not very powerful, yet we don't have cryptography, right? So it's a very pessimistic world for us. So one way to interpret our result is that Pesiland is actually even worse than what we previously believed, because not only NP is hard in Pesiland, but also TFNP is hard in Pesiland. All right. So in what remains, I'm going to try to give you a proof overview. And more than an overview, this is going to give you some kind of flavor of the approach that we're proposing. And this approach is to study these problems not directly, but in fact studying a different object altogether. But hopefully the language I've been using so far kind of indicates where I was going. So what we're going to do is to introduce first a generalization of average case hardness. Okay, so both TFNP and one-way functions, we said that they could be viewed as special cases of average case hardness in NP. But now we're going to instead look at something more general. And that is going to be something we call an interactive puzzle. So what's an interactive puzzle? Well, think of it as a computer game, right? In a game, I don't just get a single challenge I need to answer, but I get a challenge and I have to move somewhere, then the game tosses some random coins, and then I have to move, and so on and so forth. So it's really an interaction between this challenger and the attacker, where the challenger is tossing some random coins in between every step. Okay? So I'll define it more formally shortly, but really think of this as an interaction. Challenger sends some random coins, sends it to attacker, attacker needs to send a message. Then the challenger sends some random coins, attacker responds, and so on and so forth. Now, it will be very obvious that in fact, the assumption that NP is harder than average is going to turn out to be equivalent to the existence of a two-round puzzle. That's going to follow mostly by the definition. And it turns out that if you consider a special class of puzzles with something we call perfect completeness, and roughly speaking, perfect completeness will say that the attacker can always win in this game. Or, sorry, well, it's always possible to win in this game. Not attacking can always, but it's always possible. In that case, those type of puzzles are going to give rise to a language in TFNP. That's hard on average. Okay, so the language of puzzles allows us to capture already these familiar notions. And the main thing we prove is a round collapse theorem for puzzles. That's going to say something like, if you give me a 7-round puzzle, I can construct a 6-round puzzle, so I can collapse rounds. And for our purposes, what we're going to show is that if one-way functions don't exist, then we can do a round collapse that in fact also preserves perfect completeness. So if the original had perfect completeness, the new one will also have that. Now you might be wondering, where is all of this going? It seems like we're doing something completely unrelated to what we wanted to do. Well, it turns out that actually, from the literature and interactive proofs, it turns out interactive proofs are very related to these interactive puzzles, as the name suggests. There are some results that can be kind of ported to our setting. And they can be interpreted as saying that if you give me a 2-round puzzle, I can construct a 3-round puzzle that has perfect completeness. Okay? So you can take a 2-round puzzle, you construct a 3-round puzzle with perfect completeness, and now you can collapse rounds if one-way functions don't exist. So the conclusion is that either one-way functions exist, in which case we're done, or it is the case that we can go from 2-round to 3-round perfect completeness and back to 2-round with perfect completeness, which gives me a hard and average language in TFNP. All right, so this was very high level. Let me now introduce the notion of interactive puzzle and then go over each of these steps a little bit more detailed. So an interactive puzzle, as I already hinted at, considers this interaction where I have a challenger that samples random coins. He picks a random n-bit long string, sends it to attacker. Attacker needs to provide an answer. Then he picks another one. Then attacker needs to provide an answer, and so on and so forth. And eventually, after a certain number of rounds, we're done. And then the challenger is going to apply some polynomial and computable algorithm on the transcript to decide whether he's going to accept or reject. We're going to go back to our 2 conditions from before that we used for average case hardness of NP. The first one, non-triviality, in this context, are going to be saying that there exists some unbounded attacker that can make the challenger accept. So if you run in exponential time, you can make the challenger accept. Okay, so that means that it is possible to make him win. But the hardness condition is going to say that a polynomial time guy cannot make him win with probability more than 1/3. Okay, so I'm taking this notion, this kind of games from before, and I'm generalizing it to many rounds of interaction, and we're just generalizing non-triviality and hardness in a natural way. Non-triviality just says there exists some way for an unbounded guy to win. It's just that in polynomial time you cannot do it. So that's what I'm going to call an interactive puzzle. Any questions? So there are 2 things that are worth pointing out. So this is very similar to something called Arthur-Merlin games defined by Babai-Moran, which are equivalent to what's called public coin interactive proofs. So they consider a very similar interaction pattern, where they have this verified samples random coins and prove a response and so on. But the difference is that we're now considering a computational soundness property. Right? In those kind of proof system, this hardness condition really was saying that non-triviality didn't hold. It just said there is no attacker that can win in this interaction, can make the challenger accept. So rather, this computational, the hardness condition we have here is in fact very, very similar to the notion of a computational soundness in the case of an interactive argument. So you can think of this kind of as an interactive argument for an empty language, in a sense. Having the property that the prover can actually, with unbounded time you can win, but no computationally bounded guy can win. Now the fact that these are very similar to interactive arguments is going to be a very good thing for us, because there's been a lot of literature studying interactive arguments, and we can leverage that. In particular, these 2/3 and 1/3 are not great. We'd like to reduce them. We'd like to get the completeness of this non-triviality, saying that they can win with probability 1 minus something very small, and you would like hardness to say nobody can win with except with very small negative probability. And indeed, you can actually amplify them using parallel repetition. Parallel repetition theorems that have been established for public coin interactive arguments. So using exactly the same kind of lemmas that are proven there, turns out that defining it with 2/3, 1/3 is the same as defining it with 1 minus neg and neg. All right, now let's get to this perfect completeness property. It's probably what you are all expecting now. We say that a puzzle has perfect completeness if this non-triviality condition actually kind of holds it probability 1, in the sense that an unbound attacker can always make the challenger accept. All right, so no matter what the challenger does, I can always make him accept. All right, so let's relate this to average case hardness. So let's look at what this looks like in the case of a 2-round puzzle. So 2-round puzzle, you sample R, answer P1, and then this verifier is accepting or rejecting. And so clearly, a 2-round puzzle directly implies a hard-on average language in NP, because this is a particular sampler, and it samples a random uniform instance, right? And your job is to find a witness. This is a witness, right? Because this is like an NP relation. So that's trivial. Another thing that's trivial is if you have some language in NP that's hard on average for uniform distribution, meaning that it's hard on average when I sample uniform random statements, then that gives rise to a puzzle also, right? Because the sampler samples a random instance. That's exactly like the first message, right? So it's exactly the same thing. And it turns out that actually NP being hard on average with respect to the uniform distribution, this is true if and only if NP is hard on average for any polynomial type distribution. This is a classic result by Pagazzo and Levin. So combining this observation, we have that 2-round puzzles are exactly identical to the existence of a hard on average language in NP. Okay. And by the same argument, we also get the existence of a 2-round puzzle with perfect completeness. This implies a hard on average language in TENP. Because what does perfect completeness says? No matter what x you send here, there exists a way to get the guy to answer yes. So in particular, for every R, there exists a P1, a witness. So therefore, this thing, a 2-round puzzle with perfect completeness, gives me, in fact, a hard on average language in TENP. All right, so the main question that we're interested in with respect to these puzzles is, do they actually generalize beyond NP? All right, we said 2-round puzzles, they're basically exactly where they are, the same thing as average case hardness in NP. But now we're considering more rounds. Does this actually buy me anything more? Is this kind of the existence of a puzzle a weaker assumption than assuming that NP is hard on average? So there have been some results before in the literature showing this type of round collapse theorems, that you can take these interactive protocols and collapse them to something with less rounds. In particular, there's a very famous round collapse theorem by Babai-Moran. But these round collapse theorem only work for information theoretically sound protocols. And now we have some that's computationally sound only. There's a computational hardness to the protocol, and it turns out that those kind of results don't actually work at all. They break down. So despite the fact that those results break down, what we show is indeed that the existence of a constant round puzzle turns out to be equivalent to the existence of a hard on average language in NP. So constant round puzzles actually don't generalize beyond NP. But if you go to more rounds, if you go to n-round puzzles, then it does. Then it becomes equivalent to the assumption p-space is not in probabilistic polynomial time. So p-space is not in BPP. So n-run puzzles is a much weaker assumption. Constant run puzzles are not. Okay, I'm not going to really focus on the second result. Rather, I'm going to focus on the first one. So the way we prove the first one is that we actually show that Babai-Moran's construction, the round collapse transformation, actually works if one-way functions don't exist. So if one-way functions don't exist, then I can take a k-run puzzle and I can transform it into a k-1 run puzzle while preserving perfect completeness. Okay, so and if you have that, then you can very easily prove this thing, that a constant run puzzle implies this, by considering two cases. Either one-way functions don't exist, in which case you can take k to k-1 from k-1 to k-2 and so on and so forth, and get it down to 2. Once you're down to 2, you have an average case hard problem NP. If one-way functions exist, on the other hand, then trivially you have an average case hard problem in NP, which is equivalent to a two-run puzzle. Okay, so in either of these two cases, we have a two-run puzzle. So note that this is a very kind of non-black box way of doing things, because I don't have a black box transformation from a k-run puzzle to a k-1 run puzzle. Instead, I'm considering these two walls of either one-way functions exist or they don't. Okay. So let me go into a little bit of more detail on what this Babai-Moran transformation is, and what makes it hard to prove such a transformation in the computational setting. And then maybe I'll mention a few words on how we can show it, assuming one-way functions don't exist. So remember, I would like to have a transformation that takes a k-run protocol into a k-1 run protocol. And I'm going to focus on 3-run protocols only. So I would like to take a 3-run protocol, and I'd like to collapse it to a 2-run protocol. And this is how Babai-Moran do it. They tell the challenger, so a 3-run protocol where first attacker sends a message, then the challenger sends a message, and then I'm supposed to respond. Okay. Now, let the challenger, instead of just picking a single message, he's going to pick lots of them. Okay, M messages and random strings. Then the attacker's job is going to be to give a single first message and then responses to all of those things. Right? So here he started by sending this thing at first, then he gets a challenge and he's supposed to give a response. Now he needs to give a single first message that works for all the challenges. Okay, transformation makes sense? And then this guy is going to accept if for all of them indeed he provided an accepting response. So what Babai-Moran show, and it's a beautiful and elegant proof, I'm going to give it here just for fun, is that if the number of repetitions is sufficiently big, in particular, it needs to be bigger than the length of the first message, which might look curious at first. In that case, this preserves information theoretic soundness, meaning that if this thing is information theoretical sound, meaning that there is no attacker that can win in this thing, even an unbounded one, then this thing will also be information theoretical sound, meaning no attacker can win. Okay, so let's go over that argument. Information theoretic soundness of this protocol means that for every first message P1, it is the case that with probability 1/3 over the randomness R here, there will not be an answer. Right? No, sorry, except with probability 1/3. There is no answer. With 1/3 he can cheat. But except with probability 1/3, there is no answer. Okay? Now, if I look at this thing when I need to provide answers to all of them, what we have is that for every fixed message P1, it is the case that with the probability over all these randomness that there exists an answer to all of them is going to be very, very small. In fact, except with probability 1 minus 1/3 to the power of m, that doesn't exist an accepting response to all of them. Right? Because I need to sample this thing. Now, this message needs to be good for this one, this one, this one, this one, and for each one of its probability 1/3. Now the thing is, he can choose this thing after seeing them. So that seems problematic. But the point is, he doesn't have that many choices of it, right? So if the probability for every fixed one is 1/3 to the m, that's going to win, that he can cheat. Even if it goes over all possible methods P1, the probability to exist one is by the union bound 2 to the the number of possible PIs times that, which is very small. Okay. So what this says is that if you have something that's information is theoretically sound, then everything is great. The problem is these arguments, none of them actually work in the computational setting. Right? And one thing that's worth pointing out is, like, the first thing that happens is this is some kind of like parallel partition when I'm running this protocol many times in parallel, and I'm doing it in order to make sure the soundness error goes down to something very, very small. Right? And we know for interactive arguments with computational soundness, we cannot hope to amplify the soundness to be that small. It doesn't go down to be exponentially small. It can go down to be negligible, but not exponentially small, and therefore will not be able to do any type of arguments like this. That's just one reason, but in fact, all of these steps kind of fail. And this is not just a failure of the proof techniques. You can actually come up with puzzles where if I apply Babai-Moran to them, it's not going to work. So here's a very simple example, just to give you some intuition. So here's a 3-run puzzle. What I'm going to do is, in the first row, I need to hash along that database. So it's a huge database. You need to hash it down. Then the challenger is going to ask you, is going to pick a random. So here's your database. You hash it down. He's going to pick a random position. Let's say 5 here, and a random bit. And you win if you, in fact, hash down a database that had that bit there on that random position. Okay, so for this thing to be a hard puzzle, you need to make sure that this hash function, this hash function needs to be collision resistant, so that when you're sending this, you're locking yourself down to this database. And in that case, you're going to lose the probability 1/2. Well, you can win with probability at most 1/2, or 1/2 plus some little epsilon, right? You're sending this thing, and he's picking a random position and asking you, please show that your database had a 0 in this position. You have no idea what he's going to say, so 1/2 is your chance of being right. Now, let's see what happens if I apply Babai-Moran to this thing. So in that case, the challenger here is going to ask me for lots of different indexes in advance. And I need to hash one database and then give all the answering openings. Now, the point here is, with high probability, he will not ask for the same index twice, at least if the database is much, much bigger than the hash. Right? So there would be no repeated indexes here. And therefore, I now just have a bunch of indexes and what the bit is supposed to be. So I can now just easily generate this database and hash it down myself. Huh? So it's not just an issue with the proof technique. It's just false. Babai-Moran doesn't work. But note here that for this to be hard, we needed this hash function to be collision resistant. So this doesn't contradict what we wanted to prove, because what we wanted to show is that if one function don't exist, then it works. Okay? So the counterexample fails, obviously, because it relied on the existence of collision-resistant hash functions. If one function doesn't exist, you can find collisions, and therefore the underlying thing wasn't hard. So I don't have time, obviously, now to go over the proof of this thing, and let me just mention that it relies on ideas that of techniques that we use in the context of parallel repetition, and in particular something called Ra's sampling lemma, and that's a lemma that was used in the case of parallel repetition of 2-prover games. And you can look in the paper for more details. So let me now just zoom up and finish and wrap up. So what we've done now is we introduced this kind of generalization of average case hardness that we call these interactive puzzles. And the main thing that we showed was that if one-way functions don't exist, then Babai-Moran transformation actually works. And that means that we can take a k-run puzzle and collapse into the k-1 puzzle while preserving perfect completeness. I didn't mention it, but in fact, it's easy to see that this transformation preserves perfect completeness also. Now, we also observed that two-run puzzles are equivalent to NP being Hardness average, and TFNP is implied by the existence of a two-run puzzle in perfect completeness. So now we're going to wrap everything up, but in fact, as I mentioned, there exists an early result that we can use, cast in our language, that says you can take a two-run puzzle and transform it into a three-run puzzle in perfect completeness. So taking it all together gets the proof for the main theorem. So we start off with NP being Hardness average. That's the same as the existence of a two-run puzzle. We can take this two-run puzzle and transform it into a three-run puzzle that has perfect completeness. And if one-way functions don't exist, we can apply this Babai-Moran transformation and now collapse it back down to a two-run puzzle that has perfect completeness. So taking this thing together, what we have is that if NP is Hardness average, then TFNP is also Hardness average if one-way functions don't exist. And that therefore gives our main theorem that NP being Hardness average implies either that TFNP is Hardness average or that one-way functions don't exist. Any questions on this? Yeah?
So, question.
Now back to your old question now. Now, if you had proven, if it was known that you can show that one-way functions imply TFNP being Hardness average, combined with this, you would have shown then that NP being Hardness average implies that TFNP is Hardness average.
Yeah, so my other question is that is your proof constructive in the sense that can you show that starting with the assumption, can you say that either this guy is a TFNP hard or this guy is a one-way function?
Yeah, so the way that the proof will go is to say, I'm going to give an instance that I claim is a TFNP instance, hard. And if you have an attacker that breaks it, that attacker actually is a one-way function. That's the curious thing. So it's actually kind of non-black box that way that the attacker is going to be the one-way function. Yeah. All right, so let me conclude. So the key idea that I've kind of used here is to rely on techniques from literature on interactive proofs and interactive arguments to kind of initiate this study of what we call these interactive puzzles. And these puzzles, as I hope to have convinced you of, it's a kind of an elegant way, I think, to generalize average case hardness in NP. These two-run puzzles really capture exactly what average case hardness is, but now we have this more, and generalization of average case hardness NP. Now, once we go to this interaction, it turns out that now we have this whole tool set that's already been developed for the case of interactive proofs, interactive arguments that we can rely on. And in particular, that's what we did. We relied on several techniques developed for interactive protocols in order to explore average case hardness for something that's not interactive at all, in fact, with just within NP. But going there relied on taking us to this interactive realm. So in the paper, we also consider some consequences, more cryptographic consequences of this round collapse theorem for interactive arguments. You can read in the paper, but that's more kind of a classic style theorem. But I think this is the more intriguing aspect, that going to interaction is also helpful for studying average case hardness within NP. And that's it. Thank you.
then this will imply the existence of a TFNP hard-on-average problem, right?
Sure, yeah. So in fact, many cryptographic assumptions, even the existence of collisions and hash functions, imply a hard-on-average problem in TFNP. So, in particular, factoring discrete log imply average gets hardness in TFNP.